Hello, everyone. Welcome back. So today we want to learn about what's called the rational zeros theorem and what it does for us. So I want to understand the concepts of it. We'll explain that, and then understand how we can use this theorem to find the possible rational zeros of a polynomial. Before we even get into that, let's kind of review what a rational number is. And that's going to be important. So a rational number. Okay. A rational number in general looks like we can call it well, we'll just use the same notation here. So letter P over Q, okay, where P and Q are both integers. Remember what an integer is. Okay, remember integers are basically the whole numbers and their negatives. For example, like, continuing, so -3, -2, -1, 0, 1, 2, 3, and so forth, going both directions. Okay, so those are integers. Okay, so basically a rational number is anything we can write as one integer divided by another, and either one of those could be 1. And actually, either one could also be 1. Okay, of course you can't divide by 0, but you divide by the others. Okay, so some examples of rational numbers over here, then also irrational numbers or not rational numbers. Okay, so any constant, any like integers are also, because integers can be thought of as, like, for example, -3, which would be thought of as -3 over 1. Okay, or it can also be written as -6 over 2. You get the idea. So that's also a rational number. Okay, also any kind of fraction, 1/3, 5 halves, anything like that. Okay, those are rational numbers, positive or negative. Okay, but what's something that's not rational? Well, something like the square root of 2. Okay, you can't write it this way as one integer divided by another, or pi. Okay, or a number like e. Okay, any number which also has like these would, a repeating decimal. I also would say one more thing. If you have like 1.67 repeating, or 6 repeating, or any kind of repeating decimal, okay, that's also rational, because that can also be written this way. But anything like this can't be. Okay, so that's going to be important in our discussion for today, understanding this what's called the rational zeros theorem. All right, so let's go back over here to the left, and understand this idea of this theorem. So what it says is that if you have some polynomial, let's recall this is kind of a general expression, general way to write a polynomial, okay, where x is your independent variable, and remember, for polynomial, all your powers, all your exponents are all whole numbers, and your constants are usually nice numbers. Okay, but here you have a polynomial like this written in descending order, where xn is your what's called the degree, the highest power, and then you have its coefficient in front called the leading coefficient, then the next highest power of x, and so forth, and down to the least highest power of x. If you have x to the first, then plus a constant if there is a constant. Okay, now if you have a polynomial written this way, here's the key is that integer coefficient. So these numbers in front, these coefficients are integers. Okay, they can't be, in this case, they can't be rational numbers like 1/3 or 5 halves, or irrational numbers or anything like that. Okay, then every rational zero of this polynomial can be written as a rational number. Okay, P over Q, where P and Q are both integers. Once again, that's what it means to be a rational number. And P is a factor of this constant A0, and Q is a factor of the leading coefficient. And once again, assume both those are non-zero. So once again, P is a factor, any factor, positive or negative, of the constant, and Q is any factor, positive or negative, of the leading coefficient. Okay. Now, what this means, if there is a rational zero of P, of this polynomial, then it can always be written in this form. Now, that just kind of tells us there is one. It doesn't necessarily tell us how to find it. What we can do is we can get an idea of what rational zeros are possible by using this theorem. Okay. Now, a few notes about it. Now, what we'll do is actually say we can find all those numbers that fit that. We can find, assuming a(n) and a0 are integers, we can find all the possible rational numbers, all the possible numbers that would fit that, okay? But there's no guarantee that if there is a zero, it's going to be one of those. We're just saying if it is a rational zero, it's going to be one of those. And also, any irrational zeros or any complex zeros, zeros involving I, are not included in this, only rational zeros. Okay, so let's take a look at our first couple examples. Start with some basic ones, some from kind of simpler power expressions, and kind of build up with this. So once again, we're talking about the rational, some examples. Okay, what we want to do is find the possible rational zeros. Okay, so find the possible rational zeros. All right, so number one, let's start with a basic one. So let's say our function f of x is x squared minus x minus 6. Okay, so here's how this is going to, how this will work. How is I going to use this theorem? All right, so our leading constant, our leading coefficient, and once you make sure it's in ascending order, your leading coefficient, this is a second degree polynomial. The leading coefficient is number in front of the x squared term. Call that a(n), and a(n) is equal to, obviously, 1. Okay. Now, if you look at factors, possible factors of a(n), okay, this is what we talked about being q. So what could q be? Well, q could be just plus or minus 1. Okay, both those can be factors of that. So it could be only be plus or minus 1. That's a simple one. Now, a0 is the constant, which is 6. Okay. Then the thing about factors of it, that's what p is. Okay. That's once again, this is q, this is p. And think about the factors of 6 also include plus or minus 1. Okay. And I'm putting plus or minus, even these could be plus or minus. Other factors of 6 are 2, 3, and 6. Each one could be positive or negative. Okay. So the possible rational zeros of f of x are given by p over q. And those are, so just simply divide all these by each one of these. In this case, there's only 2. And here, so that's going to be possibly could be 1 over 1. And here I'll only write one, each numerator and denominator could be plus or minus, but that's just going to lead to 1 plus or minus out front. Okay. Plus or minus 2 over 1. Okay, we're dividing each. So dividing this one by 1, dividing 2 by 1, plus or minus 3 divided by 1, and then plus or minus 6 divided by 1. Okay, and of course, just simplify those. Those are plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. Now, remember what this tells us is these are possible rational zeros of this function. Okay, none of these are guaranteed to be zeros. It could be other zeros. Okay, because it's possible if it has irrational zeros or complex zeros, zeros involving I, they're not going to be in this list. And also, it doesn't mean all these are zeros. It just means if there is a rational zero, it has to come from this list. Okay. Now, actually, it turns out how you do this then, how you'd find out is it a zero or not, is to test it. So let's take a look at the next part back over to the left. So using the rational zeros theorem to find the rational zeros of a polynomial function, find the possible rational zeros is what we did. Okay. So what we do is test each one. We're not going to do all of them because that would be testing 8 different possibilities. But for example, you could test each one. So how we do that, for example, we start here, f of 1, okay, is 1 squared minus 1 minus 6. And that's going to be just 1 minus 1 minus 6, which is minus 6. And this is not a 0, okay? Because our answer to be a 0 has to be 0. To recall, a 0 is anything that makes your f 0. That's obviously not a 0. Okay. We can do the same thing with -1. Okay. Expect it won't be either, but we can plug it in. So -1 squared minus -1 minus 6. This would be 1 plus 1 minus 6, which of course would be -4. Also, this is also not a 0. Okay. Now let's get to something that is a 0. Okay. Let's try f of 2. That was another one on our list. Plug that in. So 2 squared minus 2 minus wait, no, actually, let's do -2. My mistake. Yeah, let's actually do -2. So I don't have to spend too much time on this. This one will be 0. So -2 squared minus -2 minus 6. It turns out this one will be a 0. And so it's going to be +4 plus 2 minus 6, which is 0. So this is, so x equals -2 is a 0. Okay. So that's what we can do is you can actually test each one, plug it in, and remember to be a 0, you plug it in and you get 0 for your answer. And so that number is a 0. Now, actually, let's graph this one. And actually, we'll see it as this actually has 2 zeros. So as we'll see, if you tested actually +3, it would also be a 0. Okay, let's graph this. Y equals x squared minus x minus 6. Okay, and our zeros are x, same as x-intercepts, -2, which we just found out, and also 3. So out of that list of 8 possible rational zeros, only 2 were. And we expect to have only 2 since it's a quadratic function. Expect to have 2 at most. Okay. So what this, once again, the value of this theorem is it can find out if there are rational zeros. Remember, integers are also rational. These are integers. That you can, it's actually got to be in that list, but at the same time, it doesn't tell you which ones are. And also, if there are other kinds of zeros, irrational zeros or complex zeros, it also doesn't tell you that either. Okay, let's look at another one. Number 2. So f of x is equal to, let's see, x squared minus x plus 6. Okay. Now this one, if you notice, this one would actually have the same. Okay. So here, my a(n) number in front of my leading term is 1. A(0) leading term is 6. This would have the same possible zeros as number 1, as the problem for number 1. Okay. But let's actually graph it. I think we're going to see that actually none would be. Okay. So if I just, let's actually just, let me just copy this, copy it, and paste it, and just make this a plus. Yeah. Okay. That's what I wanted to see. So actually notice this one is entirely above the x-axis. Okay. So what that means, there are no real x-intercepts. Okay. So this one actually has no rational zeros. Okay. But this f of x has no real zeros. That includes rational zeros. Basically, what that means would have complex zeros. Okay, it has to have 2, basically be both complex. So basically, you have to involving square root of I or square root of -1. Okay, so once again, what this means, you'd have the same possible zeros, possible rational zeros as this. So it would be what this says, theorem says, if you have rational zeros, we come from this list. But as I said, in this case, it had the first one we did had 2 from that list. This one would have none in that list. Okay. Let's take a look at number 3 down here. All right. Let's say I do this. How about this time our f of x is equal to, how about 2/3 x squared plus x minus 3. Okay. Now this is meant to be a trick question, but actually this one here, you notice my a n is equal to 2/3, and this is not an integer. Okay. So if you look back at our theorem, oh, what on earth? Let me get rid of that. That was bizarre. Let me go back and so not an integer. Why is that important? Well, in our theorem, we said that if a polynomial, this polynomial has integer coefficients, so the number of coefficients have to be integers. This one's not an integer, so in this case, this rational theorem, zero theorem, that doesn't apply. Okay, so in this case, it doesn't apply. Now, it doesn't mean it doesn't apply, it doesn't have rational zeros. It just basically, we can't do this. We can't do the same thing. Okay. Now, let's take a look at a number 4. Let's do another basic one. Okay, so this f of x is equal to x squared minus 5. Okay, now, same thing. This is our, it's in descending order. Our leading coefficient, an, is going to be 1 again. Our a0, our constant term, is going to be -5. And so once again, think about factors. Well, the factors of 1, once again, this is our q. It'd only be plus or minus 1. And once again, here, if we factor this, okay, our p could only be plus or minus 1 or plus or minus 5. All right. So once again, our possible rational zeros are, so p divided by q, and that's going to be, so divide each one of these, so be 1 divided by 1. We have plus or minus 1 divided by plus or minus 1 again. It's still just 1 plus or minus, okay? And then plus or minus 5 divided by 1. Of course, that's just going to be plus or minus 1 plus or minus 5, okay? Now, is either one of those a 0? Okay, are any of these, so we have 4 possibilities. Are any of those zeros? Actually, no. All right, actually graph this one. Y equals to x squared minus 5. It turns out these numbers right here, okay? It turns out those numbers are, those are not rational zeros, okay? Now, the way to find this, if you actually set this equal to 0 and solve, our zeros of f of x are x equals plus or minus the square root of 5, okay? So this one has, so in this case, so this f of x has no rational zeros. Okay, this one has no rational zeros. So all this theorem says, if it has rational zeros, it would have to come from this list, these plus or minus 1, plus or minus 5. In this case, this one has no rational zeros, which can happen. So that's one of the things I said. So if the function has other zeros, it doesn't account for that. Okay. Let's take a look at one more. So give me just a minute to decide which one I want to look at next. Okay, let's look at this one. This should be number, I think, number 5. Okay, this time our f of x, so let's call it f of x, doesn't matter, is going to be 6x to the 4th minus x squared plus 2x plus 12. Okay, now this one's going to be a bit of a pain to list all these. You'll see why, but this is a good example of what, the possibilities you can have. Okay, so once again, it's in ascending order. All right, so our an, our leading coefficient, obviously is 6. Now think about the factors of 6. I'm having trouble writing today. Okay, this time that's going to be your q. So think about the positive 6. Well, 1, of course, 1 goes into 6. Everything goes into 6. 1, also 2, 3, and 6 are all factors of 6. So factors of q could be plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. Now, what about 12? Well, a0 is 12. Think about the factors of 12. Actually, all the ones we just listed for 6 are also there. So plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6, then also finally plus or minus 12, since 6 is a factor of 12. Okay, so now if we think about our possible zeros, possible rational zeros, okay, so what we're going to do then is we have to divide each one of these, okay, I'm sorry, each one of these by each one of those, okay. Possible zeros are p over q, okay, and those could be, right, so divide each one of these by 1, so plus or minus 1 over 1, plus or minus 2 over 1, plus or minus 3 over 1, plus or minus, oh crap, I forgot one. And also, sorry, plus or minus 4, okay, left one out, sorry about that. Plus or minus 4 over 1, plus or minus 6 over 1, plus or minus 12 over 1. All those were reduced, but see, that's just, and so this is just one set, okay? So now, also equal to, so now divide each one of those by 2, so plus or minus 1/2, plus or minus 2 over 2, which of course we reduce, plus or minus 3 over 2, plus or minus 4 over 2, which should also reduce, plus or minus 6 over 2, and plus or minus 12 over 2, which would, some of those were reduced, and some of these are repeating, so you can always get rid of the repeating ones, okay? Then divide each one of these by 3, okay? So plus or minus 1/3, plus or minus 2/3, plus or minus 3/3, and so on. So you see what we're doing. So you see that this is a lot of possibilities. I said some of these are repeating from ones we had before. Plus or minus 12/3, for example, plus or minus 12/3 is 4. We've already seen 4, okay? But still, you get the idea of how many this can be. So this can be possibly, if it was, what this is saying, once again, if you have rational zeros, have to come from this list. And so we're still not done with the list. So now divide all these by 6. So plus or minus 1/6, plus or minus 2/6, plus or minus 3/6, plus or minus 4/6, plus or minus 6/6, plus or minus 12/6. Okay, now that's a lot. Once again, as I said before, many of those will reduce, some of those repeating, like 2 over 2 is 1, and 3 over 3 is 1, 6 over 6 is 1. But still, that's a lot, okay? And once again, so those are your possible rational zeros. All this means is that if you have rational zeros to this function, they have to come from this list. But it doesn't guarantee that those, you do have zeros in this list. You may have other zeros. You may have irrational zeros. You may have no real zeros at all. That's the advantage of this thing. You know, the irrational zeros have to come from this list, but you don't necessarily know which ones are, if there are any at all. Okay. In fact, if we graph this one, okay, y equals 6x to the fourth minus x squared plus 2x plus 12. And actually, if you notice, kind of like the one we had a minute ago, this shows it doesn't cross the x-axis, therefore it has no real zeros. Okay. So you can imagine you have to go through all this list, test all these, and to find out that none of them work. But if you want to check, you have to test plus or minus 1, plus or minus 2, plus or minus 3. You know, test each one and see if actually it turned out. In this case, f of x, this fx has no real zeros. That means it has, we expect it to have, since it's a fourth order polynomial, we expect to have 4 zeros, no more than that. And it will have 4, though some may, that means they're all complex and some may repeat in a complex way, but basically it has no real zeros. So no rational zeros. So basically you would actually have to go through that list and you find out nothing actually worked. So why are we doing this? Well, explaining this is another example of something in math that was really valuable a long time ago before calculators and computers, before people can graph functions. If you wanted to know, once again, what this function, let's go back to Desmos, you know what this function looked like, graphing it, you know, would take a lot of time. You have to plot a lot of points, you know, graph it the way a calculator or graphing computer does. So basically you did things like this and other techniques involving other algebra and calculus to get an idea of what the graph actually looked like without having to go through and plot, you know, hundreds of points or plug in hundreds of values, hundreds of values, to get a good idea of what the graph looked like. So these techniques, even though it's kind of tedious today, were really valuable at one time in math, but not as much today now that we can graph things. Okay. So what we've learned is that basically about the rational zeros theorem, what it tells us is that if we have a polynomial, let's give a polynomial like this, where our coefficients, the numbers, the a's, numbers in front, including the constant, are integers. If it has rational zeros, it has to be one of these, p over q, as we've seen, where p is a factor of a constant, q is the factor of a leading coefficient. Put those together, it has to be one of those if it has rational zeros. And once again, as it says, there's no guarantee that any one of those numbers, any of the numbers, is a zero. And it doesn't include, it also doesn't tell you anything about any irrational zeros or complex zeros. But finally, then if you want to test and see if this is zero or not, once you get that list of possible zeros, you plug them in and see if plug them into your function. If you get a zero result, that number is a zero. So that's what this theorem then tells us. Thank you. Have a good day.